to introduce Retinoscope, our explainable AI platform for early retinal anomaly detection. So retinal diseases like, for example, diabetic retinopathy and macular degeneration affect over 400 million people worldwide. The problem we are trying to solve is two-sided in the sense. The first one is diagnosis often relies on specialized clinicians, which creates access barriers, especially in, let's say, underserved regions where people do not necessarily always have access to. The second side of that is, even when we have access to those, let's say, clinicians and clinicians and infrastructures, the interpretation can be very slow and inconsistent sometimes, and it could be actually resource intensive too. So the problem we are trying to solve right now is clear. It's basically, how can we make retinal disease detection both faster and accessible without having to sacrifice accuracy and, say, trust in the results? So our solution is something called Retinoscope. It is a medical vision analytics platform. It uses deep learning to analyze retinal scans and provide explanation and transparent results. So unlike other AIs that may be in the same field, our Retinoscope basically emphasizes on why it made a certain decision through generating heat maps. So you can actually see why the model chose a certain disease over another one. In that sense, think of it as an assistant for the clinicians. It's basically an assistant, but not a replacement. It's just to make their jobs easier while keeping them in control. So what are the features of this model? So you can detect 6 major retinal diseases with high accuracy. So those diseases are right here: the diabetic retinopathy, opacity, glaucoma, macular edema, macular degeneration, and retinal vascular occlusion, including a normal state, which we refer to as, say, the normal eye. So including that, so that would be seven conditions in total. So it integrates also seamlessly into workflows because it's simply an app or a website that you can use anywhere and everywhere. So it's very efficient and very compact. You just need even a simple phone. You just need that one in order to be able to use it, which requires really low resources there. So the technologies, the tech stack we used is, under the hood, the Retinoscope has convolutional neural networks that work with something called the GLCM. The GLCM is the gray level co-occurrence matrix, which is basically used to capture certain patterns. So the point we're using GLCM in this context is that it will help us, let's say, capture different textures or different colors that we might miss if we use only convolutional neural networks. And it has been trained on over 3,000 images with being split among those different diseases. And then the data set is also in balance, so we do not have biases towards one and not the other. So it has been able to achieve 91% overall detection accuracy on partial matrices. So that simply means that when the model outputs something, because it's all probabilistic, it outputs a matrix of the diseases with confidence rates. So that just means that if we have 7 diseases, the model has actually been successful in predicting at least 4 out of 7, which is very valuable. And for perfect matches, that is actually 70%. So that means it is actually 70% accurate in predicting all the matches, 7 out of 7 in accuracy. So that's what a Grad-CAM or a heat map would look like that the model generates in order to explain its decision. As you can see, it's focusing on certain areas and not other areas, which would be very helpful to a clinician to actually analyze and less time consuming. So the data set integration for the bot is that we're using this exactly 3,200 fundus images, and then 2,700 retinal images, and then around 600 normal cases. So Kaggle is where I've been able to actually parse the data from, and it was from, it is a public data set that everybody can have access to. And in the future, if this project gets even bigger, maybe we can parse data from a lot of different places, which would make it very robust, which would make it very more accurate and more reliable. And it is also not in balance because it's relatively low, because for each classes, the amount of images is always between 400 to 600-ish. So it's not, yeah. And then we're using something called transparent learning, which means that the model has technically being built on top of another one, which is ResNet 50. So in my case, I'm fine tuning the 4 layers of ResNet 50 in order to let's say support MIMA predictions, in order to detect the colors and the edges and the shapes from that ResNet 50 model. And plus that, if I include the GLCM as a feature, that would make it very more, let's say, reliable. So and so in practice, Retinoscope helps in 2 ways: early screening and decision support. So early screening, by that I mean detecting diseases at stages where treatment is the most effective. And for decision support, I mean giving clinicians confidence through transparent explanations. We see this as a way to actually extend the reach of eye care, especially in regions where specialists are scarce. So for market potential, the market for AI-driven clinician solutions is projected to grow from 2.2 billion to around 9.4 billion by 2030. With aging population and rising rates of diabetes and other different diseases, the demand for early, reliable screening tools is only going to increase. And Retinoscope positions itself as the intersection of this innovation and clinical trust, which is where adoption will truly happen. And as you can see, this is a graph it's a picture of how it would grow nearly 4 times it, or 3 times it. So our roadmap is clear. In the short term, we are working on clinical validation studies with let's say okay. So in the midterm, we aim to extend the portable fundus camera. We aim to expand to portable devices and let's say internet-less devices, so for people to be able to use the app actually offline and not needing to access a certain website or something, which would make it even less resource required and even more accessible to people. So, uh, so my bad. So to close, Retinoscope is about more than just AI. It's about just giving doctors a transparent and trustworthy assistant and giving patients the chance for early life-changing interventions. And this is if you guys have, let's say, your smartphone is closed, you can scan this QR code in order to actually test it with me, which would be very cool. You can just scan this one. Or for the purpose of this presentation, let me just do it live. So this is an overview of what the website looks like. If you want to see the documentation, you just click view on GitHub. If you want to try it live, you try it right now. It's live on Streamlit. So let me try with CERN for this image, and you'll see. So as you can see here, it generated a heat map, which means with the redness being focused on the middle where the disease is actually currently present, and it detected retinal vascular occlusion primarily. But alongside with that, with the retinal vascular occlusion, it also has macular edema and less confidence rates for these ones. And it is actually downloadable if you want to download it and analyze in softwares like Excel. That is also doable. So this would be the interpretation. But if you want it as a report format, you can show report, and in that case, it would generate a report for it. So as you can see, the same heat maps, and it would graph those confidence rates so as to clearly see what is standing out and what is not. And then the same confidence rates, we can see that the ones standing out, the primary disease found is macular edema and retinal vascular occlusion. And then these will be the notes. And we also have a disclaimer here stating that this does not replace a clinician's, it's just here to assist it.